In this section, we examine how Azure App Service Plans form the backbone for hosting web applications, mobile backends, and RESTful APIs. Building on earlier topics, such as ARM templates and bicep files, the focus here is on provisioning and configuring a dedicated environment for app services. App Service Plans define the compute resources reserved for an application, such as memory, CPU allocation, and scaling settings. By understanding these options, administrators can ensure sufficient resources, optimize performance, and improve cost management. They also enable unified deployment processes when combined with Azure virtual machines or container-based workloads. Because app service plans form a central resource grouping, it is essential to understand their role in the overall Azure environment. Administrators gain efficiency by consolidating multiple applications under one plan, provided they share similar performance demands. This approach highlights a fundamental resource management strategy in Azure, leveraging shared capacities to optimize both cost and infrastructure usage. App service plans are tied closely to Azure App Service instances, dictating performance capacity and underlying infrastructure. At a high level, they outline necessary CPU cores, memory allocations, and storage availability. When an application is deployed into an app service plan, all instances share the specified resources, making the selection of an appropriate tier crucial for performance. The configuration includes the number of VM instances meant for running the workload, allowing administrators to adjust scale considerations. This approach contrasts with serverless models where resources are abstracted further. In essence, the overall functionality of an Azure App Service Plan forms the engine that powers web applications or APIs deployed to that plan. Effective planning requires accurate forecasting of user traffic, data processing demands, and memory allocation to prevent resource congestion. By analyzing workload intricacies early, administrators set a solid foundation for application performance. App Service provides distinct tiers: free, shared, basic, standard, premium, and isolated. Each tier includes unique resource commitments, scaling features, and network configurations. Historically, free and shared tiers are suitable for smaller workloads, prototypes, or personal experimentation. For production workloads, basic, standard, and premium tiers offer greater resource capacity, scaling options, and custom domain support. Premium further enhances availability and performance, enabling extra features such as integrated network isolation or advanced scaling. Isolated tier extends these attributes to segregate workloads entirely, beneficial for scenarios requiring stringent compliance or dedicated hardware. Administrators, when planning their environment, map application objectives against these tiers. The selection of an app service plan tier also influences the cost and potential updates. For optimum usage, it is vital to evaluate how the environment scales based on real-world traffic, the number of concurrent users, and the application's complexity. This consideration improves resource alignment and overall budget strategy. When deploying an app service plan, it is important to consider its relationship with other Azure resources. Because an app service plan is created within a specific region, all applications assigned to that plan must run in the same location. Administrators should plan for this constraint, especially if they're targeting global user bases or require geographic redundancy. Additionally, resource management extends to the subscription and resource group level, where an app service plan can be moved or cloned for environment migrations. Drawing on preceding concepts in this course, such as ARM template usage, helps ensure consistent configurations and version tracking via infrastructure as code. By combining these strategies, organizations maintain a reproducible deployment process that supports advanced management scenarios like region failover or cross-subscription transitions. Adhering to resource management best practices further enhances organizational compliance, cost transparency, and operational agility within Azure's distributed ecosystem of services. When provisioning an app service plan, administrators can deploy using the Azure portal, command line tools like Azure CLI or PowerShell, and automated methods with Azure Resource Manager or bicep files. The Azure portal approach offers guided steps, making it suitable for quick tests or initial exploration. Command line methods, powered by Azure CLI or Azure PowerShell, streamline the creation process through scripts, enabling repeatable deployments. Meanwhile, infrastructure as code techniques, introduced earlier in this course, allow for robust configuration management and version control of app service plans. Templates outline parameters such as pricing tiers, region, and tags, ensuring consistent deployments across multiple environments. By maintaining these definitions in a centralized repository, organizations strengthen change management controls. Each approach has benefits, but together they form a flexible toolkit for provisioning and controlling app service plans in line with an organization's automation preferences and governance policies. As part of Azure's focus on repeatable cloud deployments, Azure Resource Manager templates and bicep files are integral strategies for setting up app service plans. Within these templates, administrators can codify details such as the tier, size, and scaling rules. This allows the infrastructure team to confidently redeploy or update an app service plan in multiple environments without deviating from the original template. ARM templates rely on JSON, while Bicep offers a more concise syntax. Both integrate seamlessly with DevOps pipelines, ensuring continuous integration and continuous deployment (CI/CD). By parameterizing certain values, like region or SKU, teams can adapt a single template for different production or staging scenarios. Moreover, combining these templates with other Azure services, such as container instances or virtual machine scale sets, enables advanced multi-tier architectures. This approach fosters a consistent development lifecycle, reducing deployment errors while promoting security and compliance through repeatable definitions. Scaling an app service plan relies on a balance between performance requirements and cost considerations. Horizontal scaling increases the instance count to distribute workloads, reducing load on each instance. Vertical scaling adds more memory or CPU power to the existing instances, changing the app service plan's pricing tier or SKU. Integrated auto-scale rules leverage metrics like CPU usage, memory utilization, or request queue lengths to trigger scale-out or scale-in events automatically. For mission-critical applications, scale rules are configured to ensure minimal latency during peak times. However, each new instance increments overall cost, stressing the need to analyze usage patterns carefully. Hybrid approaches can combine horizontal and vertical scaling, optimizing resource utilization. This agility aligns well with cloud-native design principles that emphasize elasticity in meeting fluctuating demand. Properly configured app service plans can dynamically allocate resources, sustaining performance under unpredictable workloads while preventing unnecessary infrastructure expenses. App service plans incorporate security features to safeguard data, networking, and code execution. By default, traffic to applications is protected via TLS, enabling secure connections. Administrators can further integrate custom certificates and domain names for production environments. With a premium tier and higher, features such as virtual network integration become available, allowing secure connectivity to on-premises networks or other Azure services through private endpoints. This removes exposure to public internet routes, reinforcing enterprise-grade security. Additionally, application settings for secrets or sensitive data can be stored securely in Azure Key Vault, ensuring they are not embedded in plain text. Role-based access control, RBAC, also plays a critical role, allowing organizations to limit who can modify app service plan settings or scale parameters. Collectively, these security practices reduce the potential attack surface. They also allow for secure interactions with various Azure resources used to store data, authenticate users, or provide advanced logging. Visibility into the performance and status of an app service plan is critical for responsive administration. Azure App Service includes built-in diagnostics for capturing detailed logs on request flows, application events, and platform-level data. Administrators can enable features like Application Insights, which provides deeper telemetry, such as distributed tracing and custom event tracking. This tool is beneficial when diagnosing issues under load or troubleshooting performance bottlenecks. Logs are stored in Azure Monitor Logs, centralizing data collection for simplified analysis. By correlating logs from multiple resources, such as container instances or virtual machines, teams gain holistic insight into the system's health. Alerts can be configured to notify administrators when threshold values are exceeded, facilitating proactive interventions. This continuous monitoring loop underpins the DevOps practice of continuous improvement, ensuring that an app service plan remains stable, performant, and capable of enduring evolving business demands. When integrated fully, it fosters data-driven decision-making throughout the application lifecycle. App Service Plan costs correlate with selected tiers and the duration of active instances. Free and shared tiers are low-cost options, but come with limited production viability. Basic, standard, and premium levels scale in price with increased resource allocations, advanced networking, or additional dev/test environments. Premium v3 and isolated instances are costlier, but offer advanced capabilities, including private endpoints and higher resource limits. Additional features, such as custom domain SSL certificates, can add to the total expense. Administrators should periodically monitor usage data and adjust their plan tier or number of instances to optimize cost efficiency. This requires analyzing application workloads to see if the resources allotted match actual consumption. Combining these insights with Azure Reservations or Azure Hybrid Benefit can yield further discounts. Cost analysis becomes particularly relevant when managing multiple interrelated services, making it important to allocate budgets accurately and forecast potential growth scenarios in alignment with organizational objectives. As organizations mature in their Azure deployments, automation emerges as a central theme for efficient operations. PowerShell scripts and Azure CLI commands provide an accessible framework for automating tasks related to App Service Plan provisioning or scaling. Through scripting, repeated actions, such as creating multiple environments or updating plan configurations, become consistent and reproducible. Integrating these scripts within DevOps pipelines allows administrators to incorporate checks, environment validations, and rollback options. With scheduled scripts, operators can dynamically adjust scaling rules or apply new settings based on usage analytics. These automated routines reduce human error and expedite application deployment and maintenance cycles. Additionally, referencing best practices from earlier sections regarding infrastructure as code, one can embed the scripts into ARM templates or bicep files. As a result, the entire lifecycle, from creation to teardown, becomes systematically defined, further simplifying governance, traceability, and collaboration among cross-functional teams. Optimizing an app service plan for performance involves aligning resource allocations with application demands. Administrators can implement connection string caching, employ minimal overhead logging, and leverage asynchronous programming to prevent bottlenecks. Ensuring that compute resources are appropriately sized, both vertically and horizontally, avoids under-provisioning or over-provisioning. Utilizing pre-production testing environments, such as staging slots, can help identify performance constraints before changes impact users. Furthermore, advanced features like Azure Front Door or Traffic Manager facilitate global load distribution, minimizing latency. The premium and isolated tiers offer specialized hardware for high-performance scenarios, improving throughput. Monitoring tools such as Application Insights or Azure Monitor deliver real-time metrics on response times, CPU usage, and dependency calls. By correlating these insights with deployment events, teams can isolate performance dips and optimize accordingly. When combined with DevOps best practices like blue-green deployments, organizations can fine-tune performance without enduring outages or extended maintenance windows. Provisioning an app service plan is best approached with a foundational strategy. First, define application requirements, the expected traffic, data processing needs, and geographical considerations. Then, select an appropriate tier by balancing cost constraints against performance metrics. Include capacity for short-term spikes, factoring in auto-scaling rules set on relevant usage indicators. Next, codify the setup in ARM or bicep templates, ensuring reproducibility and version control. Incorporate essential security measures like private endpoints and RBAC to safeguard access. Integrate monitoring tools early for robust diagnostics. By referencing earlier lessons on container deployments, administrators may combine containerized workloads with app service for additional flexibility. Use environment-specific configuration settings to isolate dev, staging, and production phases. Maintain continuous reviews of cost and performance data, adjusting tiers or scaling parameters as usage evolves. These steps produce a stable, secure, and scalable foundation for hosting web applications, APIs, and services within Microsoft Azure.